We're going to move on to our second session of this. This session is the science of carbon credits across the oil and gas sector. We're very fortunate to have Caroline Normal joining us, a senior policy advisor from the Bipartisan Policy Center. And she'll be here to moderate and introduce our speakers. So welcome, Caroline.
Thank you, Rebecca. I'm really delighted to introduce the session to panelists, as Rebecca noted, who will be providing their expert insights on the technical challenges and opportunities for generating carbon credits in the oil and gas sector. So with that, we'll first hear from Mark O'Mara. Mark is a senior scientist for global methane with the Environmental Defense Fund. And I'll turn it to you, Mark.
Thank you, Caroline. I appreciate the opportunity to speak today and delighted to be here with all of you to discuss some of the key learnings from scores of previously published research over the past decade on the assessment of methane emissions from the US oil and gas production sector. Next slide, please. So very briefly, the US oil and gas production sector is incredibly vast and complex. We have over 800,000 actively producing wells, which collectively produced more than 40 trillion cubic feet of natural gas and more than 4 billion barrels of oil in 2022. The map on the right is a heat map of oil and gas production from all US wells. The warmer colors show production hotspots. And what we see here is this remarkable diversity in the basin level production profiles. For example, we see significant oil and gas production in the Appalachian Basin and in the Permian and in the Bakken in North Dakota, but comparably less production intensity in basins like the Uinta in Utah or San Joaquin in California. And all of these differences in basin level production characteristics have implications for basin level methane emissions. Now, nationally, about 80% of all of the wells are low producing wells. What that means is that they are marginally economic and produce less than 15 barrels of oil equivalent per day. And even though they are so many, they only produce about 6% of the national total energy production. And as we will see in a couple of slides, these are an important source of methane emissions nationally. Next slide, please. So estimates of national methane emissions from the production sector come primarily from three methodological categories. The most commonly cited estimate is, of course, the EPA Greenhouse Gas Inventory, which uses an emission factor approach and reports around 3.5 million metric tons of methane from oil and gas wells. And this represents about 0.6% of the total gas produced is lost to the atmosphere via methane emissions. The second is estimates based on component level measurements. And these indicate that the production sector emits around 7 million metric tons, so about a factor of 2 greater than what's reported in the EPA inventory, and represents about 1.3% methane loss rate. And then third are estimates based on ground-based facility level measurements. So instead of looking at components, we are now looking at a facility's total methane emissions. And these studies report about 8 million metric tons of methane emissions, equivalent to about 1.5% methane loss rate. So there have been recent research that I have been a part of that synthesized hundreds of ground-based facility level measurements and found that about 4 million metric tons, or roughly 1/2 of the total methane emissions from the oil and gas production sector, is attributable to the emissions from the numerous low-producing well sites in the country. And the study also revealed that this population of well sites have significantly higher methane loss rates of more than 10% of their production. So this is a really unique methane mitigation opportunity given their numerous, given how numerous they are in the country. And then finally, we are now seeing rapid advancements in remote sensing capabilities, including the use of drones and aircraft and satellite remote sensing that have already produced some very interesting data on total supply chain methane emissions at the basin level and at the national level, although sector-specific estimates are currently not available at the national level. Next slide, please. So in the next few slides, I'm going to summarize the key findings from the literature on methane emissions from the oil and gas production sector. The first is that based on measurements, both at the component, equipment, and facility level, each producing well site, so whether it's low or non-low, whether it's an oil or a gas well, has a potential to emit methane emissions from both unintentional leaks, so things like valves, fittings, and connectors, as well as intentionally vented sources, like from pneumatic devices or from tanks. So the chart on the right shows the equipment level estimates for natural gas systems in A and petroleum systems in B. And what we see is this range of about less than 0.1 to 1.5 kilograms per hour, or about 1 to 10 metric tons per year per equipment. Next slide, please. We also see this sort of wide range in measured facility level methane emissions. So the figure on the left shows actual measurement-based data for facility level methane emissions for several US basins, focusing on the low producing well sites. And again, what we see here is a range of less than 0.1 to more than 10 kilograms per hour per site. The figure on the right is a compilation of nearly 1,200 facility level measurement data from 8 US basins. On the y-axis is the percentage methane loss rate, and on the x-axis is the natural gas production rate. The most interesting finding here is that lower producing wells emit a considerably larger proportion of their production compared to higher producing sites. Now, some of this relationship is explained by the fact that some fugitive methane emission sources continue to occur throughout the life cycle of the well, even as production rapidly declines. But there is also a potentially important factor here linked to the likelihood that higher producing wells are better maintained than low producing well sites. Next slide. One of the consistent findings in the literature is that there are high emitting methane sources from a small fraction of total sources, so about 5%, that tend to account for a disproportionate share, or about 50% of the total measured methane emissions. What this means is that if we went out today and randomly took measurements at 1,000 facilities, about 50% of the total measured emissions will come from just about 50 facilities. In other words, the methane distributions tend to have a long tail characterized by these high-emitting facilities. And recent snapshot measurements from area remote sensing have reported extreme facility level emissions that appear to be highly intermittent, where the frequency of occurrence varies significantly depending on the basin. And in the next slide, this sort of variability in emissions is really evident also when we look at total basin level emissions. And so, for example, here, what we see is that the Appalachian Basin has the largest methane emissions from low producing wells. So it accounts for about 30% of the total, compared to other basins such as the Barnett, which is region 5 in this map. And one important factor here is simply the scale of low production activity, where we find the largest basin level population of old and low producing, and by our estimate, very leaky wells in the Appalachian region. Next slide, please. So to put it all together, here are some main takeaways. Each well site has a potential to emit methane emissions. The large population of low-producing well sites is as important as the non-low-producing well sites in terms of their total national methane emissions and represents an important methane mitigation opportunity here in the US. Comprehensive methane emission measurements is going to be key, not only for characterizing current levels of methane emissions, but also for tracking progress toward emissions mitigation. And as I mentioned, aerial and satellite remote sensing, particularly if they're able to quantify both total area emissions as well as high emitting sources, have a key role to play in helping elucidate the magnitude and the scope of the methane emission problem while catalyzing or supporting effective action toward mitigations. And then lastly, because of the stochastic characteristics of emissions, effective management of these emissions requires routine or continuous emissions monitoring to quickly identify and fix anomalous methane emissions events. I will stop here, and I look forward to further discussion on this. Thank you.
Thank you very much, Mark. And just a reminder for the audience to prepare questions, which we'll take at the end of all of the speakers' remarks. Next, we'll hear from Mary Kang. Mary is an assistant professor of civil engineering at McGill University. Mary, turning to you.
Sorry, can you hear me? Okay, so thank you for the introduction. Next slide, please. So, oh, back to the first slide, please. Okay, so the title of my talk are Abandoned and Orphan Oil and Gas Wells, Methane Emissions and Beyond. In terms of beyond, I'm mainly going to be talking about a bit about groundwater contamination potential. Next slide, please. So a lot of what I'm going to be talking about today is motivated by the methodology for the quantification, monitoring, reporting, and verification of greenhouse gas emissions reductions and removals from plugging orphaned oil and gas wells in the US and Canada by the American Carbon Registry. And I did contribute material for this ACR methodology, some of which was included, some of which was not. So I'm not here to endorse, sponsor, or recommend this methodology or to do the opposite, but I will refer to this methodology a few times during my presentation. Next slide, please. So first, I do want to talk a little bit about the definition. So here's a definition from a recent publication. Orphan oil and gas wells are a category of unplugged non-producing wells for which the operator is unknown, unavailable, or insolvent, leaving no responsible party to plug the well and restore the well site other than government agencies and the general public. So that financial, so there's another table at the bottom kind of breaking it down. And I think I want to draw your attention to two columns. One's the plugging status. So orphan wells are unplugged, abandoned could be plugged or unplugged, and then financial responsibility. So orphan wells are the wells where the responsible party is not the operator because they're not available. Whereas abandoned, the responsible party is the operator. There are some definitions where abandoned wells, orphan wells, are a subset of abandoned wells, so it can be quite confusing. But that's why I wanted to lay these out here. Next slide, please. But regardless of whether the well is an abandoned orphan well, they are a structure that goes through multiple geologic formations, including groundwater. A lot of what we're going to be talking about are the methane emissions right at the ground surface of the well. There could be gas migration and emissions elsewhere as well, and of course impacts to groundwater. Next slide. I'm not going to go in depth into this figure here, but I do want to say that the methane emission rates vary by many orders of magnitude, and I'm not even talking about temporal variability yet. In this particular publication, we found high emitters are gas wells that are unplugged, but there was also this special category of plugged and vented wells that were also high emitters. Next slide. I just said that gas wells are likely to be high emitters. Well, we did a literature review, and basically that's not always consistent. So if you look at the far right of the conflicting results area, whether the well was producing oil, gas, or both, it's conflicting whether it's a predictor of high emitters or not. The only thing that we found was kind of consistent with geographical area, which encompasses all kinds of factors that are geologic factors, but also engineering and policy related factors. But in general, more studies are needed, and we don't really have the ability to come up with a predictive model to estimate what the emission rates might be. Next slide, please. And these are quotes directly from a recent publication noted here. And the point is, we do need orphan well specific emission rates. Currently, methane emissions from abandoned wells are assumed to be representative of orphan wells. It may be true, it may not be true, but we need to evaluate the differences in these emission rates between orphan wells and all abandoned wells. And then we can determine orphan well specific emission rates, which may or may not be very different from abandoned wells. Next slide, please. So there are a lot of data limitations. And this is a figure for documented orphaned wells in the United States. And, we need these well attributes because if we want to identify high methane emitting wells, we need to do this kind of data analysis. So here are just three availability of three important data types: well type, well depth, and last production date. First of all, a lot in the red, and even this one kind of in the middle, there are a lot of attributes that are largely unavailable. So that's the first point. The second one I want to draw your attention to is on the far right is the last production date. So even when you have the data, okay, so say we have last production date for 16% of the documented wells. And then if you look at that data, you can see it's very biased. So most of the last production happened between 2010 and 2020. So it's most likely be quite biased, because if we had all the 100% of the last production date, my guess is that distribution that you're seeing at the bottom right will look very, very different. Next slide, please. I'm not going to go into detail about variability, other than to say, we found some studies that show, well, emission rates of high emitters appear to vary less over 2-3 years. So this is, but definitely an area requiring further research. Next slide, please. But understanding this variability, I'm not going to be talking about variability, but rather to say it's important to understand this variability. So this is specifically a figure from the ACR methodology that I contributed. And for carbon crediting, emission rates need to be stabilized. So all the green curves here would be constant or stabilized emission rates. They're good to use for carbon crediting. But if you have one of the red curves, or the trend looks something like that, they're non-stabilized, so they cannot be used for carbon crediting. Next slide, please. So how do we determine this? Well, there are requirements in the methodology to do multiple measurements. There's 2 measurements required with a 30-day minimum gap before plugging. And so there are questions, well, so is this enough to capture variations over the crediting period, which is 20 years in the ACR methodology? Next slide, please. And I do want to say the last production date, I mentioned this before, last production date for documented orphan wells available appears to be biased to our recently orphan wells. This data set was also used to kind of come up with this 20-year crediting period. So, so this is an area that needs to potentially be improved upon. I do want to say that, when we think about other, methane emissions and beyond part, so methane emission measurements at the surface does not necessarily give you an indication of the extent of subsurface impacts. whether it be to groundwater or just to the, in the soils. Next slide. And with respect to groundwater, there are also a lot of questions on which groundwater should be protected. So the average groundwater well depth in the US is 72 meters, according to a 2017 publication. But there's a lot of data showing groundwater wells are being drilled deeper. There's also evidence showing that fresh groundwater exists below base of fresh water, which is to the depth of which oil and gas regulators require protection. So there's a lot of questions about which groundwater should be protected for use today, but also in the future. So to summarize, methane emission rates from abandoned wells vary over many orders of magnitude. And I'm not talking here about temporal variability. And the identification of well attributes of high emitters remain an active area of research. Orphan well specific methane emission rates and analysis are needed. Temporal variability of methane emission rates needs to be understood for carbon crediting. And methane emissions are not indicative of the extent or potential for groundwater impacts. Thank you. Last slide, thank you.
Thank you very much, Mary. The next presentation is from Natalie Peckney. She is the technical lead for the Natural Gas Infrastructure Program at the National Energy Technology Laboratory. So Natalie, I will turn it over to you.
Thank you. So Mary just spoke a little bit about the temporal variability of methane emission rates from orphan wells. I'm going to dig into that into a little more detail. So the current funding we have for exploring orphan wells comes from the Bipartisan Infrastructure Law, which allowed the DOE to put together the catalog program, which stands for Consortium Advancing Technology for Assessment of Lost Oil and Gas Wells. So if you go to the next slide, this program, the consortium includes 5 national labs, which you see on the right, one of which is NETL. And you can see the relevant appropriations language. We're focused on identifying and characterizing undocumented orphan wells and mitigating the environmental risks of undocumented orphan wells. So this is a 5-year, $30 million program. Just to give you a little bit of background about my group's research and funding. Okay, go to the next slide. So the question that I'm going to try to address here is, what is known about the temporal variability of methane emission rates from orphan wells? And the short answer is not enough. So there have been very few studies in the literature that have focused on or even commented on temporal variability. But we do know from our observations that not all wells exhibit an emission rate that's steady over time. When wells are full of liquid, we sometimes see evidence of bubbling, which can be more steady state and kind of look like water boiling, or it can be more sporadic, almost like a burp every now and then. And similarly, when we look at wells with infrared cameras, we can sometimes see puffs of gas being emitted. So this leads us to ask, how do emissions vary on the short term? If we collect the emissions measurement over a short period of time, what risk do we run of overestimating or underestimating if the emission rate isn't steady? And then can we maybe relate that emission rate to some other parameters like temperature, barometric pressure, precipitation, or even subsurface activity, such that we can maybe model or predict emissions? And then how do emissions vary long term? Do they vary with seasonal changes? Can they be expected to decrease over time, like in the timescale of decades? So all of these questions are important to address in the context of giving and receiving carbon credits based on the emissions reductions from well plugging. Next slide, please. To address the question about short-term variability, we recently have started out doing some experiments with collecting measurements over a 2-hour period. And we're using high flow sampling, which is one of the approaches you can use for measuring emissions from orphan wells. You can see our setup in the pictures there. In the picture on the right, you can see my colleague is holding an infrared camera so that while the high flow sampler is running, we can visually ensure that all of the emissions from the well are being sucked into the sampler inlet. So we did this experiment at 5 different wells in Western PA, all of them unplugged and known to be leaking. I can share some preliminary data, but just know that we are continuing these studies at multiple additional wells. So if you go to the next slide. Okay, so here are results for 3 of those wells. So you can see that although there's significant noise, on average, the emission rate doesn't change a whole lot over the 2-hour period. So I'll note that sometimes with high flow sampling, we do see initial high reading when you first start, as the vacuum generated by the sampler initially evacuates the gas that's built up in the well. But then what follows is more representative of a stable emission rate. So when we do high flow sampling, it's important to collect the sample at least long enough to account for the possibility of that misleading high initial reading. Next slide, please. So these are the other 2 of the 5 wells. They showed a different behavior over the 2-hour experiments. So the one on the left showed a slow increase about halfway through the sampling time. And then the one on the right shows some small, more short-lived peak events. So although we're still investigating and analyzing the results here, it's likely that there was fluid in the wells and that they were burping or bubbling, like I mentioned previously, which caused this significant variability in the emission rate over the 2-hour period. So the purpose of these 2-hour experiments was to provide recommendations for the duration of a short-term measurement. Clearly, we need a larger sample size to be able to draw conclusions from and make those recommendations. But just here with these 5 wells, you can see that in general, the short-term variability was below a factor of 2. So for a slightly longer 24-hour experiment design, we looked to a study done by Stuart Riddick, which investigated 18 wells, 12 in West Virginia, 5 in Pennsylvania, and 1 was in the UK. So here, some common behaviors were observed, and Mary kind of mentioned this, but they're summarized in the graph on the left that shows emission rate over time. So wells similar to the yellow line showed an initial exponential decrease in emissions, but fairly quickly, the emission rate arrives at a stable value. The blue line shows a longer-term decrease in emission rate, and then the red and gray lines show a sudden increase or a decrease in the emission rate, after some period of time. And then, of course, the black line shows a steady but highly variable emission rate, potentially due to bubbling. So overall, these data show that wells are not limited to a typical behavior in terms of their emissions over time, and there can be high variability even over 24 hours. On the right, the graph shows these measurements compared to instantaneous or short duration measurements. So you can see on the 1-to-1 line there that there are only 4 of the measurements that fall near that line. So the other measurements are up to 2 to 4 orders of magnitude different on either side of the line. So that's quite a significant difference when you compare taking a kind of snapshot or instantaneous measurement versus doing a measurement over a longer period of time. So it really illustrates the potential for high variability temporally. Okay, next slide. So lastly, I'll share some research that we're doing about longer term variability, even longer than a 24-hour period. We did some flux chamber measurements at 7 wells that were all unplugged and known to be leaking. And here we collected data over months continuously. And the intention is to compare seasonal emission rates, summer versus winter, and look at this longer term variability. So you can go to the next slide. So we're still analyzing the results, but I'll show the preliminary results for 1 of the wells. So this is emission rate over time. The black dots are the emission rate, and then the purplish line is barometric pressure. We measured some other parameters like the barometric pressure to see if there was any correlation with emission rate. So, and this was done over the course of, if you look on the x-axis, from October through January. During this time, there's definitely significant variability in the emission rate by about an order of magnitude. No obvious correlation with the barometric pressure was observed here. And there were long periods of time, like you can see at least the 2 weeks in the beginning and the 2 weeks towards the end there, where you see definitely a lower average emission rate than what was observed in the middle, like the November and December data. Okay, go to the next slide. So what does all of this mean in the context of carbon credits? Unfortunately, much of the data that we have now are very intriguing, but they aren't sufficient to allow us to really prescribe rules or recommendations for sampling duration. I've showed you data that At NETL, we've collected for, less than 20 wells total. So we need larger sample sizes and we need more data to be able to come up with those recommendations. So obviously, longer term measurements would be more accurate in making sure that temporal variability is well characterized. But then, of course, this leads to, it takes a lot longer to do and it's a lot more expensive. So it's not really feasible for doing this for a large number of wells. We do know on the short term, care needs to be taken if you're doing high flow sampling to allow at least long enough to account for the potentially high initial reading. And then if there's any evidence of bubbling or burping from the well, then a longer duration measurements would be needed. And then on the longer term, say like weekly or monthly averages, we can see order of magnitude differences in emission rate. So ultimately, we need more data to determine how best to adequately characterize temporal variability. We've seen enough to know that an average emission rate should have a high uncertainty prescribed to it, maybe even an order of magnitude. So we'll continue to learn more about temporal variability. You can go to the last slide. There's ongoing studies at NETL and the other national labs that are participating in the catalog program. There's a link to our website there that's kind of still under development, but make note of it, keep an eye on it. We'll be posting results and new findings that we get in the program. And if you have interest in hearing more about temporal variability, or if you want to be involved in some way or collaborate in collecting the information, please contact me. Thank you.
Thanks so much, Natalie. Our final speaker for session 1 is Duane Purvis. He is the founder and principal advisor of Purvis Energy Advisors. Duane, I will be turning it to you for your presentation. Thank you.
Thank you for that, Caroline. So if we're going to prevent emissions, we need to leave it in the ground. The question is, how much is it? Now, so far from the discussion, it might be confusing. There are at least 2 large categories of carbon offsets. One is for wells that have no owner or an owner not willing to plug them, and not producing, but emitting. And there's a second class of offsets that pertain to prematurely plugging wells that are operating and are producing. Now, the dynamics in those 2 different situations are somewhat different, although they're driven by the same root fundamental physics. The good news is that the science of reservoir engineering, a subset of petroleum engineering, has learned to deal with, make estimates of what will be produced in the future next. So in the 100 years or so that we have had petroleum engineering as such, we've only developed 6 methods to determine how much is going to be produced in the future. As we move down this list, they require more data. They also give us a more constrained answer. But for late life producers, the sweet spot is there in the middle at decline curve analysis, which seems simpler than it is. The fundamental idea is really pretty basic. We're going to make a graph and try to extrapolate a trend. Now, to be clear, we are ultimately interested in the production from a whole reservoir, because by definition, a reservoir has the ability to move fluids within it, and changing the production from one well can change the production from another well. So plugging one can increase production from the other. The one element of the leakage concept TJ was talking about before. But we can make these kinds of straight line extrapolations because we understand the underlying physics of the reservoir that create these patterns. The problem is, next slide please, that the physics can be obscured. First, by data issues. This slide shows 4 wells in close proximity, all producing from the Barnett Shale. And it's obvious the significant irregularity that suggests changes in operations, and there are, in fact, some changes in operations. The green line is oil, more importantly, the red is gas. But not as obvious, next, is that these four wells actually overlay each other to some degree. The operator, for periods of time, was allocating exactly the same production to each well, or nearly the same production. That early production, highest rate, correlates to the highest rate in the later production, and the lowest to the lowest. So there is a real significant issue that we can encounter with production data. Now, just a quick orientation that I didn't give you before. This is a semi-log plot of rate versus time. Years on the x-axis and flow rate per day on the y-axis. Next. Now, this, notwithstanding the data issues, does also show several operational incidences, in which production stepped up or stepped down. But the second graph there shows a different kind of operational issue, where operations are changing, but in this case, it's causing the production to hold flatter than it normally would be. Now, if the only thing we saw in the production trends were the reservoir, we could predict that. But data issues and operational issues often overprint and confuse the matter. Next. Now, when it does come time to identify the production trajectory from the reservoir dynamics, we have lots of options of how to look at it. Here are some samples of 4 graphs, all to look at the trends. And this one's pretty well behaved. The issue there is, however, a change. It may be hard to see. In the upper right, you can see at the best around 2008 or 9, there's a pivot, there's a corner. In fact, there are like 2 steps. One is a change from an offset producer, and the second is a change in the operations of this well. So it does, there really can be a lot going on, and it's not just a matter of fitting a curve. Next slide, please. And in real life, the production trends can look really pretty chaotic. These are all real life, reasonable sort of representative samples. Now, the one in the upper left looks really well behaved, and I would say it is, except that there is a corner. There is a change in trend in the last 2 years as the light green line trends up and the dark green line trends down. Without getting into too much of the details, the point is, especially when you get into late life, we have significant issues with the production, with understanding and forecasting what that will be. Next slide. So it has to be, something that would be shutting in a producing well needs to be additional, as TJ said. And one question is the reservoir trajectory. That is a significant question. But also, late in life, there are significant questions of economics and, in fact, of mechanical integrity of the well. Next. So reserves has a technical meaning. It's the volume that will be produced over time. So if I extrapolate that trend in this example case, everything under that curve is volume that will be produced and end up as CO2 in the atmosphere. But a bunch of that production is used to offset the cost of production. So the profit that exists for these late life wells, the low producers that are good candidates for early shut-in, the profit margins are always thin. Now, if costs were no issue, the production would continue, and that could be a basis, a starting point to understand the emissions, the long-term ultimate emissions from leaking wells that are not producing. But the more important issue is that a small change, because the margins are thin, small changes in any one of our inputs can significantly change the output of the volumes that are being offset. So here I've got a small difference in the decline curve, and you can see that the well survives much shorter or much longer and produces much more volume. Next. Or the same thing can happen with costs. If my costs vary only 30%, then next slide, then the well can stay on very much longer and generate a lot more. Now, what actually happens in real life is not this clean. What actually happens is that costs and prices and production will vary back and forth, and occasionally you'll have a mechanical problem. And the mechanical problem that can occur suddenly, unexpectedly, can end the life of the well, even though it was producing and making money. So what actually happens in late life is that these wells tend to porpoise. They move back and forth with operations and with price from profitable to unprofitable. And sometimes a well will be produced even though it's unprofitable. For strategic reasons, specifically, usually to avoid plugging, wells will sometimes be maintained even when they're online, even when they're not economically viable. Next slide. So we do have some science to work from. I'm sorry, one more. That's the extra volume that would be realized. We do have some science to work from. We build it up from individual wells. There's some well-established techniques, but those well-established techniques do bear a good deal of uncertainty, even on top of the judgment that's exercised. That could be a foundation to talk about the long-term emissions from leaking wells as opposed to producing wells, but the dynamics in the long-term leak could be different. So that's about the state of what we know. Back at you.
Thank you very much, Dwayne. And thank you to all our panelists, Mark, Mary, Natalie, and Dwayne. A quick question to kick us off, and we do have some questions coming in the Q&A, which we will include. Making sense of the expert insights that each of you shared. And I know you touched on a lot of these elements, but kind of synthesizing it for the audience. How is the measurement and monitoring of emissions from the oil and gas sector currently working? That is, what measurements and science do we have? What can we learn from them? And where are the major gaps in our knowledge?
I'm happy to report that the oil industry has, in the last couple of years, gotten much more serious about measuring emissions. The next step will be to abate them better, but just in the last year or two, there's been a rapid growth in the efforts by operators to measure their own emissions. At this point, we use measurements in about 4 different orders of magnitude, and we don't always get the same answers from those different sources.
Yeah, if I could add a little to that, I think up until around the late 2000s, the predominantly used method was really the emission factor approach, where default emission factors or engineering best guesses are applied to activity data to estimate total methane emissions. This is a so-called traditional methane emissions inventory approach. Now, a modern version of this approach took it to the next level, where actual measurements are performed at specific emitting components on the site, and then the data is used to develop representative methane emission factors. And then the measurement-based emission factors are applied to the population of methane emitting components. This is the typical bottom-up approach. Now, starting in the early 2010s, new methods of emissions quantification started to be used, the so-called top-down methods. So in its most basic framework, one measures methane concentration enhancements downwind of the facility or downwind of a production area, and then uses plume transport models to compute how much methane would have been emitted from the source and at what rate, in order to explain the observed concentration enhancements. And so this approach includes measurements using ground-based mobile laboratories or using drone-mounted or aircraft-mounted sensors in using satellites. Yeah, so there are, of course, strengths and weaknesses of each of these approach, but I am particularly excited about the rapid advancements that we have seen in the past couple of years on satellite remote sensing. I think it's unlocking a lot of opportunity to be able to quantify methane emissions globally. It's not perfect, it's got its own limitations, but it's very promising in terms of being able to quantify what's being emitted where and at how much rate, and whether those emissions are changing over time.
Thank you very much, Mark and Dwayne. And then, taking that science, taking those measurements, and connecting to the markets and credit space. Another question for all of the panelists: how does this information translate into the generation of credits? And more specifically, do we have enough yet to generate or to create reliable credits? And specifically, do we have the information we need to even establish the robust baselines needed?
It's a tough question. I think as scientists, all of us would always like to have more information and more knowledge, and we want the answer to be as reliable as possible. On the other hand, there's also action that needs to be taken and needs to be taken urgently. So there is a balance going to have to be struck between uncertainty and action. And that we do know enough to take some action. If we get too far ahead of ourselves, then we risk losing credibility and losing the whole thrust of the initiative. But if we don't act fast enough, then we won't get as much done. I do think we have enough to have a serious conversation and start studying and taking pilot projects, early steps like we are seeing.
I agree. I would add to that it's just really important to make use of what is already known. And what's known about emissions from orphan wells are that they have a fat tail distribution, right? So it's characterized by these super emitters. There's going to be a large population of wells that aren't emitting or are at very low emission rates. So we definitely, to have the most impact on emissions reductions, need to find and mitigate those super emitters first, right? So we do know that. And then with respect to the accuracy in measuring emission rates, I think it probably is just a matter of assigning uncertainty to those values, right? Like if you're using a particular emissions measurement approach, we still don't have a lot of information about how one methodology compares to another. What's the time frame over which the measurement should be taken? There's some general recommendations, but there's still a lot of uncertainty. So if you were able to say, we measure the emissions at this well to be 10 grams per hour, but it's going to be plus or minus, 50 grams per hour or 100 grams per hour or something like that, where you can still have a quantifiable answer, but you're taking into account that there's uncertainty in that value.
I don't know if I have time to just to add to that. These are all good points. Just to add to that, I think there's a fundamental difference between estimating emissions at a statewide or a national level scale, because you can come up with an average, and then you get some wrong, but overall maybe they average out. You get some overestimates and underestimates, they average out. For the carbon credit, you're trying to get emission rates at a specific well. So I think it's a harder question to answer. Like, it's much harder if someone asks me, what is the rate at this particular well? That's very hard than to say, well, in general, what are the range of estimates for abandoned wells in Canada, or like some very general question. I think that's an important nuance to mention here with respect to carbon crediting. The other point that I would say is there is a cost consideration. And I believe this is important for project developers in terms of what technology they use to do measurements. So it's a balance between how accurate and how good your estimate is versus the resources available financially, but also technologically and so forth.
Completely agree with what Mary just said. There is a clear distinction between our ability to quantify methane emissions at the facility level versus quantifying at the regional basin level or national level. And that's important. There are technologies, and we're seeing advancements now in measurement technologies that could allow quantification at the facility level down to about 2 to 5 kilograms per hour. But that's going to leave out a lot of these low producing wells whose emissions may be a lot lower than that. So the detection limit still remains a challenge, particularly for area remote sensing of facility level emissions.
Thank you very much. Really, really helpful insights and given us a lot of food for thought, particularly around translating the science and the challenges therein that each of you spoke to. With regard to some of the methods in the market space that session 3 will focus on. So thank you each very, very much for your time and your expertise. And I'll turn it back to Rebecca.
Yes, thank you all. This has been great so far and really appreciate your expertise. If you see a question in the Q&A that you think you could address through typing an answer, I welcome the panelists to go ahead and do that. I think there are a couple of clarifying questions about people's slides. We are going to go to a break for the next 15 minutes. I'm impressed with how well you all have stayed to your time. So thank you very much. And we'll be back at 1:35 to go on to our next session.